Hi, my name is Andrew Sapupo, and my research is about engineering magnon-phonon interactions in a yttrium-iron-garnet crystal for quantum information applications. Now, I know this sounds like a mouthful, but I'm going to break it down piece by piece, starting off with why this research is useful. So in this picture, we see the transistor for a modern-day computer, and the way it works is that electrons flow down this path through the gate where they could be represented as a 1 or a 0, and then out the other side. So basically, electrons transmit data through movement. However, if we're able to combine magnons and electrons in this modern-day chip, it will greatly boost its efficiency. It will allow us to pack more data into smaller space and read and write RAM much faster. And the way this works is that, as mentioned, electrons need paths to flow through in order to transmit data, whereas magnons transmit data through changing magnetic fields. So all the space these paths take up can be filled in with magnons, greatly increasing the data density of the chip and thus making it more efficient. So some of you may be wondering why we do not do this now, but to understand that, we must first learn what a magnon is. A magnon is a quantized particle of a spin wave, similar to how a photon is a quantized particle of an electromagnetic wave. And spin waves you could think of as waves of oscillating magnetic moments of individual particles. And spin waves can only occur in magnetic materials. So what this means is that if we imagine a material like iron, and we zoom in on it to see an infinite plane of iron atoms in front of us, each one of these atoms will have its own magnetic field and its own magnetic moment vector. That is represented by the purple vector, the purple arrow. So the purple arrow will point in the direction of the north pole for each of these atoms. So in this infinite plane of atoms in front of us, each one of these atoms will have a purple arrow pointing in the vertical position initially for all of them. And when this material is brought in the presence of an external magnetic field, all these arrows will start to rotate or move in precession around a central axis, as shown in this figure, the top figure here. And in the bottom figure is what we see when a bunch of these atoms undergo this process, and this is known as a spin wave. And spin waves generate magnons. Why we care about magnons is because they're very easy to encode data into. We could encode vast quantities of information into them by simply changing the properties of the external magnetic field applied to it. The downside to magnons is that they do not last long enough for practical utilization in the chip mentioned on the first slide. And that's where phonons come in. Phonons are quantized particles of lattice vibrations, or in other words, sound waves. We could also encode vast quantities of information into phonons, but it is much more difficult to do so than with magnons. The advantage to using phonons is that they could be engineered to have far longer lifetimes than magnons. So if we could combine the best properties of both of these particles, magnons with their easy tunability and encoding data into them, and phonons with their long lifetime, we will have a practical method for creating the chip mentioned on the first slide. And this is known as the field of hybrid magnonics, encoding data into magnons because it is easy to do so, then transferring that data to phonons since they could last longer. And that brings me to the goal of my research, to maximize magnon-phonon coupling, or in other words, maximize the data transfer between magnons and phonons. And to do this, we need to use a material known as a magnetoelastic material. And this is a material in which, when exposed to an external magnetic field, it will vibrate, thus producing both magnons and phonons already coupled inside of it. And the material we have chosen for this is a yttrium-iron-garnet YIG crystal, as shown here and here. And also as shown here, current methods use a very thin YIG, about 0.2 micrometers thin. And we propose if we increase the thickness of this YIG crystal, therefore it will increase the coupling strength since there will be more space in the crystal for coupling to occur. And also, as mentioned, we want to engineer the lifetime of phonons to be as long as possible. So once the coupled phonons are produced in YIG, we will transfer them to a material better suited for confining them, GGG, a gadolinium-gallium-garnet. And remember, all phonons are is just vibration waves. So once these vibrations are produced in YIG, they will be moved to GGG and start to bounce around inside this material. So the idea is to come up with a structure of GGG that could efficiently confine these bouncing waves for as long as possible. And current methods use a rectangular GGG to do so, where the vibration wave enters here travels through the material, hits this straight edge and rebounds, having diffraction losses out the sides of the material. This means that some of the phonons will be lost out the material, and thus the lifetime of them will be decreased. To combat this, we will also be exploring various different geometries of GGG in order to minimize this diffraction loss. However, we will not address this until we determine if increasing the thickness of YIG does in fact increase coupling strength or not. And to do this, we have two methods to do so, where the first is the analytical method, where we use elastic wave theory and Christophel's equation to come up with an expression that relates our YIG-GGG system to coupling strength. We want to create an equation where we could input various different geometries of our system, and for that equation to then tell us if the coupling strength increases or decreases based on those geometries. So to start off, we use Christophel's equation, where this is the density of our material multiplied by its acceleration equal to material-specific constants times the stress and strain values of that material, stress and strain being related to the pushing and pulling forces of that material. So after we solve this equation through many simplifications, we get our second equation, which represents the displacement of the phonon at any point in time, or in other words, the shape of the vibration wave. And why this equation is useful is because it allows us to solve for the third equation, the magnetoelastic energy, UME. And why we want UME so badly is because it is directly proportional to GMB, which is the coupling strength term that we want to maximize. So through the second equation, it will give us the variables ux and uy, and all the other variables are not as important right now. Just know that the second equation gives us ux and ui, which allows us to solve for UME. And based on if UME increases or decreases, that will tell us if the coupling strength increases or decreases. So following this method, we get our final equation, which is the one I said we wanted to solve for initially, where the coupling strength, GMB, is equal to an expression that is directly dependent on the geometry of our system. So out of all the terms in this equation, I want you to only focus on S and D. Sorry about that. I want you to only focus on S and D, which represent the thickness of GGG and YIG respectively. So, like I said previously, current methods use a very thin YIG of about 0.2 micrometers. So now we could check if 0.2 micrometers maximizes this coupling strength. So to do that, I graph my GMB equation, and we get this result, where coupling strength is on the y-axis and YIG thickness is on the x-axis. And 0.2 micrometers, as we see, falls around here on the plot, which is not at the theoretical max coupling strength. So that means there's room for us to increase the thickness of YIG. And we want to increase it to about 0.3 micrometers, and that's because that's where the max coupling strength occurs. And we don't want to increase it too much because then it will fall off drastically. But if we do increase the thickness to about 0.3 micrometers, we will potentially see an increase of 18% in coupling strength. So, which is great, but this method requires many simplifications. So to help aid us in these simplifications and to help check these results, we have a second method, which is known as the computational method. And in this method, I will simulate various different structures in COMSOL multiphysics software using a finite element analysis method. And why this method is so good is because it doesn't require as many simplifications as the previous one, therefore making the results slightly more accurate. Additionally, how this will work is that I will come up with various different structures of my system, varying the thicknesses of GGG and YIG, and then I will perform simulations of vibration waves going through them. And then I will check if the coupling strength increases or decreases based on those geometries I input. And here are just a couple of my results from these simulations. And on the left-hand side, we see one of these structures I produced. And for the most part of my simulations, you see all green surfaces, all yellow, or it's spotty multicolored. But here specifically in this simulation, we see bright blue and bright red bands. And these represent the peaks and the troughs of the vibration wave within my structure. And the reason why we could see them so clearly is because the coupling strength is high enough in the structure I've created where the vibration waves can be visualized in simulation. And this specific simulation is known as a longitudinal phonon mode. And all this means is that the particles of the mode, particles within the wave, move in the same direction as the wave. So if we think of a sound wave in air, air particle hits the one in front of it, sends the next one flying, and so on. Same principle that's going on in this simulation. On the right-hand side, we have a shear phonon mode, and all this means is that the particles in the wave move in a perpendicular motion to the motion of the wave. And how we visualize this is if we think of a stadium wave, we have people's hands are the particles, and their hands move up and down, and the wave moves around the stadium, around the arena, perpendicular to the motion of the hands. And why we care about shear versus longitudinal modes is that shear are shown to increase coupling strength more than longitudinal in the equations. So following all these results, for my future steps, I will perform these simulations over, but instead of varying just the thickness of YIG and GGG, I will also vary the entire geometry of GGG as well in order to decrease that diffraction loss I mentioned previously. And with these simulations, I will specifically search for the shear modes that they produce, since those are shown to increase the coupling strength more than the longitudinal ones. And once I have the structure that produces these shear simulations, I will take the constants that created that structure, plug them into our analytical equations, and then solve for that magnetoelastic energy term, since that is shown to be directly proportional to the coupling strength. And once I have all this information, I will then solve for the coupling strength directly and see by how much it increased or decreased by exactly. And then I will repeat these steps over and over until I could find the structure that maximizes completely the coupling strength. And lastly, I would like to thank my mentor, Manoj Satapalli, and Dr. Sangamitra Nioji for helping me with this research. Thank you. Any questions?